On the second item, we've got a frame with 2 pin connected members A, B, B, C. There's a fellow down here who is holding on to a rope that wraps around a pulley, and that pulley is attached to a 2 kilonewton weight. And then we also have the self-weight of member BC acting at its center of mass, 1.6 kilonewtons, halfway along its length. AB is considered to be weightless. You see the angles of inclination. You go look at that pulley, and so with the person pulling down to keep that weight in equilibrium, you got 2 and 2 on either side of the pulley. That means you got 4 newtons that are needed for equilibrium of the pulley, and that means in terms of the frame, what it sees is a 4 kilonewton load pulling down at point B, along then with that self-weight of 1.6 of member BC. Recognize that AB is a 2-force member. That means that when we've been asked to find our 2 reaction components, AX and AY, that AX is going to end up being equal to the force in member AB times cosine of 37 degrees, and AY is equal to AB times sine of 37 degrees. Can't say that about CY and CX. We don't know what the angle is that those 2 would resolve along to, because we don't have a 2-force member over there. Right? But we can simplify this problem in the initial setup. And so let's go get member BC in and start getting some forces laid out on this thing, on this body. We got the 4, that's the applied load up there at B, and we got the self-weight, 1.6. We've got then our CY, our CX that are unknown, but we're trying to find them, and then we've got the force in the member AB. So let's see what we can do here. If we were to some moments about point C, we could find AB directly. And so let's go give that a whirl. Some moments now about C. Say clockwise is positive. And I'm going to decide that I'm going to slide AB all the way down to a place where it intersects this horizontal line coming from C. That means that I get a right triangle that's formed. Here it is 4 meters high. Right? We've got 4 meters from this point over to C, and so then we just got to go figure out, with that being 37 degrees, what this distance is from there to there. Right? And that's going to be opposite over adjacent equals tangent, so that's going to be 4 over tangent of 37 degrees, or equal to 5.308 meters. Right, that's going to be useful, because now we can break up AB back at that location. When we do our sum of moments about point C, we can take the vertical component, which is going to be the sine of 37 degrees, so AB sine of 37 degrees is, you know, we don't really care, do we? Because we don't care what the force in the member is. We only care about what AY is, and AY is equal to AB times sine 37 degrees. So why not just go AY? That's going to translate down to here, right? Times its momentum, about C, of 9.308. You're going to say, AY doesn't act there, it acts over at A. But guess what? AY was exactly equal to AB sine 37 degrees. I can slide that AB force all the way anywhere I want to and get to along its line of action, that is, and I get back over here to this fictitious point that we could call point D. And so it doesn't matter that point A is somewhere else, and I can move that right on over. Right? So then we get minus 4 kilonewtons times 4 meters minus 1.6 times 2 meters is equal to 0. Solve that, then we get 19.2 divided by 9.308, and it's going to be 2 and change. 19.2 divided by 9.308, and we get 2.063 in the direction we got shown. That's, of course, newtons. We can then some moments about we can sum moments about point D, can't we? Because when we do that, AB goes away, CX goes away, and we can get CY. We like that. Let's take counterclockwise positive. We'll have a moment arm of 9.308 for CY. And then we get minus 4 times the moment arm 5.308 minus the force of 1.6 times the moment arm 7.308. Right, we got to get the 5.308 plus the 2. That's going to be equal to 0. We don't need the CX nor the AB in there. And so now we would solve that and find out that CY is equal to 3.537. Pretty cool. All right, now we can go take a look at summing moments about another point where we could slide AB up to another point. Let's call it point E. And so CY goes away, AB, and we'll get just CX. We're going to need this total height. That total height, that's 9.308, opposite over adjacent. So that's the smaller one. We want 9.308 times tangent of 37 degrees. And that is going to be 7.01 meters. So when we sum moments about E, then we'll get, let's take clockwise positive. We'll have 7.014 CX minus 4 times 4 minus 1.6 times 2 equal to 0. So again, we'll get 19.2 divided down by 7.014, and we get then CX equals 2.737. Right. Let's check to see if our AX is going to work out right. It should be the opposite of the 7.737, but we know from over here that, let's see, here we've got our AY, there's our AX, and so our AX would equal AY over tangent of 37 degrees equals 2.063 divided by tangent of 37, and I'm a little nervous. What are we going to get? 2.737, opposite of CX. Excellent. So that means we got equilibrium. That way we can check our sum of forces in the Y. I have done so already, and I know that it works. So I'm not going to repeat it here. But I did actually do so. So we get, for our answers here, AX equals 2.737, which could really properly be rounded up to 2.74. Acting to the right, we've got AY equal to 2.063 kilonewtons. Acting up, we've got CY equal to 3.537 kilonewtons. Acting up, and we've got CX equaling 2.737 kilonewtons. Acting to the left, and as I say, it's probably one too many digits to be included in our answer.